Welcome to this sixth video on the ConfirmaXL design system. This time around, I think we're going to shake things up a little bit. We're going to design a phase lock loop, and we're going to do so not with transistor level circuits, but we're going to use blocks, behavioral blocks that come in behavioral libraries that ship with ConfirmaXL. In previous videos, what we did was we generally open schematics and we hit the simulation buttons and we plotted the results, and we got a bit of a tour around certain features of ConfirmaXL, but we didn't do any actual schematic assembly. So I thought this time around it would be nice to show folks how you assemble, how you find the blocks, how you drop them down, how you connect up the wires, how you prepare your schematic for simulation, and as a ways of coming up to speed on the design flow. So for those who aren't familiar, ConfirmaXL is composed of third-party point tools, primarily point tools that are open source or they're free, but you can also plug in paid tools as well, so depending on your needs. So it runs on Windows 10, 11, but it has utilizes a shared folder concept, so it can cross into Linux. You can set it up to work with your Linux-based tools. It's very flexible that way. We've used it for many years in that way. We've used it with tools like Calibre well, actually, I think that might be available on Windows now. I'm not quite sure, but you're not shackled to one operating system or another. We try and take advantage of the best tools that are out there. Um, there's actually tools that are only on one operating system or the other. I mentioned Calibre, but on the Windows side, there's new tools that you would like to be able to leverage. There's a new spice simulator, qspice. I think I showed in the last video how we can simulate with qspice. At any rate, you can plug in pretty much. You can plug in a wide variety of tools to meet your needs. So we're going to get going here. And the other thing I'd like to point out is we're using an updated version of Confirma XL compared to the versions that were shown in the previous tools. So that's the other aspect of this. I'd like to show off a little bit of the features where we've made some improvements. So let me jump ahead. I'm going to jump ahead, and I'm going to show you this schematic, test bench schematic of a phase lock loop. It's a behavioral phase lock loop, and this is a finished schematic. I've already simulated it. It works fine. I thought I'd show it to you first, what our goal is, and then we're going to recreate this, and hopefully I'll hook everything up correctly and it will simulate successfully. But if you look at this, you can see, I'll show you a quick tour around this. This is a phase frequency detector, behavioral phase frequency detector, a charge pump, loop filter. It's a behavioral VCO. This is a behavioral analog block that's used to convert, I'm using it to convert sine waves to square waves, and the square waves are then used to drive this behavioral divider, which is a divide by 8. And then that closes the loop, and the divided VCO comes back here, and it drives back into the VCO clock input of the phase frequency detector. On the lower left here, we've got a pulse generator that emulates like a crystal oscillator clock. There's a power supply set up. That's 1.8 volts, and the node is labeled VP for power. Uh, let's see, I think we're running at 125 megahertz here as the reference. Again, the output is 1 gigahertz. Divide by 8. The loop bandwidth is set to 2 megahertz, and the phase margin on the loop is set to 65 degrees. And the charge pump current is set to 50 micro. That's done via this reference current source here. So if you go through the loop calculations on those top level specs, you'll wind up with values for the loop filter, and those values turn out to be a resistor value of 15 kilo ohms, and then there's two caps in there. There's the primary cap, the larger one, C2, 23.7 picofarads, and then sometimes we refer to C1 as the jitter cap. That's smaller, and that turns out to be 1.2 picofarads. So that is a quick tour. If you're curious how we actually go about doing that, we have a phase lock loop synthesis tool that's in a companion software called Silicon Psychic. It's not released yet. I use it on the prototype. We're still testing it and we're polishing it, so it's not quite ready to be released within ConfirmaXL. But hopefully it will be coming and you'll get to use it yourself. So I put in the top level parameters and it calculated all these values for me. So that's how we arrived at the parameters of the loop. So with that said, let's see here. I'm going to go and pull up another schematic here, and this is what we're going to start off with. So it's very similar on the left-hand side to the completed PLL. I thought I would jump ahead and put some circuits down there, some behavioral circuits down there, so I wouldn't have to put every single block down there, and the demonstration wouldn't take quite so long. There's also another schematic I wanted to pull up here. So I'm going to go to the ConfirmaXL library manager, and I'm going to pull up this schematic here. So this is the library manager. We updated it a little bit compared to previous videos. This is my current working library folder. If I click on any of these schematic names, test bench names, whenever you click on that, that gets popped over to the this area here, the source schematic text box. So I'm going to pull up this one here, I think. No, actually, that's not the one I want. I want this one. So this is a PFD with some other circuitry on there. Let me open it up. So this is how you would tend to open up test benches from Library Manager. So we've got this test bench schematic. Let me close that. And the reason I wanted to quickly turn to this is I've been seeing a lot of complaints among Cadence Virtuoso users about how long it takes schematics to open up these days on IC6. And some people are reporting it can take more than a minute to open up a top-level schematic. You can see that this opened up in just seconds. And so once you open up a test bench here in ConfirmaXL, it's very easy and quick to turn it over to the simulation cockpit. And I'll just show you for the benefit of some of the the Cadence users. Things don't have to be that way. So you can see I just did this pass to Confirma command. So this test bench has been passed over to Confirma. Oops, excuse me. So the name of the test bench now appears here. So PFD, so KGF behavioral PFD underscore basic, that is now, that resides here. So that's the test bench that's come over. You can see that it's come over properly. And then you do choose analysis. Let's open up all the simulation statements that had been previously saved. When it loaded, it also loaded up the extracted net list, but we're going to go ahead and re-extract that from the schematic just to make sure what we have there is fresh. Um, previous videos, we simulated across a variety of different spice simulators. We're going to stick to topspice for this one, though, I think. So we're all set. We got our schematic is loaded. The net list is there. The simulation commands are there. So we'll just say sim now. Okay, so that launched the simulator and it started and it's simulating. But we're going to just stop that. I'm going to say no here, no. Basically, is all I wanted to show in this case was just how quickly you can load your schematic and then you can simulate it. And you can recall your previous simulation settings and so forth. So that was the purpose of that. I'm going to shut that schematic down now, and we're going to go back to the test bench where we're going to assemble this new phase lock loop. So let me go ahead and pass this over now as the active test bench. So pass to Confirma, generate. Okay, you can see it came over just fine. Has the right name now in the Confirma cockpit. Let me close this, get it out of the way. And like we did before, we're going to do choose analysis. There's some previous simulation settings already there. So I'm going to open those. And say OK here, and we're going to check. I want to check to make sure that let me re-net list that again, just to make sure, and I'll hit sim. Okay, so All right, so that started. I know I have the simulation settings, a very small time step here, so that would take a long time. So we're going to just say we're going to stop this. No, no. Okay, maybe I will open up the plots to see what it's doing. Since I had saved this already, I think there's a previous okay, yeah, that is okay. So let me explain this a little bit. So what we have here is we have the phase frequency detector. It's being driven by a reference clock here, comes from this pulse source, and then there's an additional pulse source here that's driving, that's emulating the divided down VCO. So those two inputs are into the behavioral phase frequency detector, and then the outputs are tapped off and they go through this little feedback here. And this helps, this is used to set the reset delay in the phase frequency detector. And that's to, if you're familiar with phase lock loop design, that's to eliminate a dead zone that you sometimes see in charge pumps if you don't have that. So the two outputs here, this down and up plotted output, that's the output of the phase frequency detector. And let's take a little bit of a look there. I'm going to zoom up real quick here, and so you can see the up down here. One pulse is a little bit wider than the other, and so the difference in time in these two rising edges, that turns out to be uh, the the error. What would be the error, the delay between those two reference clock and divided VCO inputs. Um, so really, I just wanted to make sure that our initial circuit that we're starting off with is working okay, and it does seem to be working okay. The other comment I'll make is um, our behavioral libraries, we have behavioral schematic symbol libraries, and depending on the simulator that they use, they may reference different behavioral text libraries, spice text libraries. So here we're using topspice, and we're using topspice gate primitives. And so when you look at the output waveforms, this is the state of the gates essentially inside the PFD. So you don't see voltages here. You see high, low, high, low. If it was in another simulator, we may be using behaviorals where those outputs would show voltages. So we do that so that our symbol libraries will work across different spice simulators. So ConfirmaXL keeps track of which simulator that you're targeting, and it ensures that the right behavioral reference uh, library um, gets selected when sending the overall net list to the simulator for simulation. So hopefully you followed that. I'm not sure I even did. So anyway, so let me continue on here. So we've got the start of this phase lock loop. We got the PFD in there. I'm going to go ahead now and drop down a charge bump, I think. So let me go over here. So this is where you add symbols in KiCad. So if I select that, that pops up the choose simulator tool, excuse me, choose symbol tool. And I'm going to look in a library where I believe that uh, behavioral charge pump um, lives. So let me see here. I think it is here in this PLL behavioral library. That's going to be moved, by the way. So let's see if I can find the right charge pump. I believe this is the one. Okay, so if I go and I'll drop this down. Okay, so it's dropped down. Now I have to hook up all the wires. And the wiring tool is this one here on the right-hand side. This is add a wire. Now, if you go one more down, that's add a bus, but we're not adding buses. In fact, we don't use this for buses in KiCad for Confirma. We have another mechanism to specify the bus. So we always use the simple wire command to make connections, whether they're single wires or they're a bus. And I'll show a bus another time, I think. So let me connect this up. Okay, and we're going to have a reference current source, and we need a ground here. V end is for ground, and oops, I close that a little too soon. Let me put a net on here and a net on here. So you always have to have, for any symbol, you have to make sure each connection has a net. Otherwise it won't be net listed correctly when you're trying to generate your Spice net list. It's not just KiCad that deals with that, but we used to use I guess it was Mentor DX Designer, and that had a similar issue. So I'm grabbing this ground. So we're going to copy that. So I did Control C and then Control V, and that pulls that same. That's one way you can copy symbols from one area of your schematic to another. So let me finish that connection. And it looks like we need the reference current source now. So let me go here. And one thing you should know is for spice primitives, you always want to take them from the Confirma DXspice. So you always want to use the Confirma libraries for your spice primitives. So I go down here, I'm looking for iSource. This is a current source. And let me hook it up. There we go. And this has to have a current of 50 micro. So I'll pop that in there now. There's no AC value. We're not doing AC simulation, so I'll leave that like that. 0, and let me copy another ground symbol and I'll hook it up. Okay, and you'll notice this says I question mark. So the reference, that's the reference designator. So we have to, as you go along, you have to, or you should perhaps update the reference designators on your symbols. So the way you do that is there's this ref des tool up here. So you click on that and you say annotate, and now the I question mark is I1, and this one here is it was U question mark, now it's U2. Okay, so I still need to put a power supply pin on here. The power supply is VP. So it's connected in a symbol that further down on the schematic. I'm going to copy that. Oops, and just as we did before, Control C, Control V, just like a word processor. Oh, let's see. All right, let me save the schematic, and I'm going to go over to ConfirmaXL. Here it is, and I'm going to regenerate the hierarchy. And you can see a couple of more blocks popped up. So we've got the PFD, we got the charge bump. There, I think this reset block, that's this guy here. So any symbol where the symbol type is a schematic that says SCH, that means there's an underlying schematic for the block. And for symbols that have hierarchy, that's a hierarchical symbol, they always show up in this hierarchical navigation tool on ConfirmaXL. So that's how you go up and down the hierarchy, and you can view schematics that the blocks point to. So I've showed that in the past. I won't focus on that too much. But I think what I will do is it's nice to once in a while check as you're putting down new blocks. It is nice to check once in a while and make sure that the blocks you're dropping down are okay. So there's this feature. So we have this cell. I clicked on this cell, U2. I want to see what that cell netlist looks like. So I'll do C netlist. And so this is the spice netlist that corresponds to that behavioral charge bump. So that tells me, if that succeeded, okay, and I can take a glance, a look at it, and it looks pretty good. So I think we're okay. That block is fine. And if it's in the library, it's probably been checked out. Although that's not 100% true. So a word of caution there. So there we have our charge pump. I'm going to drop down a couple of more cells here. Let's see. I want this V source here. I think I'm going to drop down. Oops, I didn't mean to do that. I meant to hit R to rotate. So we did R rotate. And I'm just dropping this voltage source, this 0 volt voltage source. Its only purpose is to allow me to measure later on the current that comes out of the charge pump when the phase lock loop is simulating. So that's the only purpose of this block. So next up is the loop filter. So I think the loop filter is in the behavioral library. So we're still organizing some of these libraries. So there will be some updates along the way, but eventually you should have access to all these behavioral blocks that I'm showing you now. So let me go to the behavioral loop filter. Okay, there's a couple of different versions of them. I want this one. Okay, we drop down the loop filter. I'll put it right there. And let me hook it up real quick. Okay. Need a ground here, so I'll just copy the ground symbol that's already on the page. So one thing you should know, this is important too, is just like all the other Spice primitives have to come out of the Spice library that comes with ConfirmaXL, as does the ground symbol. So don't use the ground symbol up here on the interface. Use the ground symbol that's in the DXSpice library. That's important. At some point, we'll probably make this one work as well, but it does not currently. So here's the loop filter. There's an underlying schematic. You can tell SCH colon. These are the parameters that are passed into the underlying schematic. So let me update these with the correct values. The R has to be 15 as we calculated before. This C here has to be 23.7 puff. This one here needs to be 1.2. Okay, so hopefully I did that okay. Maybe I'll move this over. If I highlight it and I hit the M key, that will allow me to move that text around so we can see things a little bit better. Okay, so that's that. And I think I'll drop down the VCO next. So let me go get the VCO. And I think that's in the behavioral PLL. There are a lot of blocks, and sometimes it can be a little bit challenging keeping track of where they all are. We tried to organize them according to function, though, so hopefully our selection makes sense. So let me connect up. So this is a VCO, behavioral VCO that can be used for loops with single-ended control on the control side. This is the control side. Or sometimes we build loops with differential filters. So this would work for that as well. So in this case, we're using just the one side, and I've connected the other side, the ground. Now, on this side, this is the output. Now, this particular block, it outputs sinusoids. So it's differential, there's out and out bar, and you'll get a sinusoid out of that. So we'll have to do some wave shaping later because we're going to drive a digital divider. So I have to set up the VCO parameters, and I think I stated already that our intent is to do 1 gigahertz. So the free, this is the free running frequency, that's 1 e to the 9, 1 gigahertz. The free running voltage, so when this is at 1 gigahertz, that 1 gigahertz applies, um, I'm going to set that to 1. So when the control is 1 volt, you should get 1 gigahertz out of this behavioral VCO. And then our KVCO in our case is 140 megahertz per volt. I think this is okay. The common mode, uh, I think we can work with that. Let's see. So that should do it, I believe. If it doesn't, we'll come back and fix it if there's a problem. Um, Maybe what I'll do is I'll make the peak a little higher. So this is the peak, sinusoidal peak, the differential peak. So I'm going to set that to 2. So I think each side should have a peak of 1 volt when you make that selection. Okay, so that's that. Now we will get the next block, which is a behavioral diff comparator block. So we'll go to, I believe this one's in the behavioral analog. Um, I think I think this is the one I want. B diff comparator. Again, it takes a while to become familiar with these, but you will. I'm going to mirror this block. So mirror horizontally. There we go. And that's that. And now let me hook it up. Okay, so it doesn't really matter which output of the VCO is connected to which input of this block. In this case, either one would be fine. And while I'm here, I'm going to give this a name. I will call this So here's the add label, add net label. So that's one you want to be familiar with. So I'll say this is VCO output, this will call P for positive. Go ahead. And then this next one I'll call VCO output N negative. VCO N. Okay. So I'm not the fastest in wiring up schematics, but I think we're getting the job done. So now I want a divider, and the divider that I want hasn't been moved over to the behavioral library yet. Uh, it exists here in this one. These are sort of still undergoing some tests across all the simulators to make sure that they work okay. So SIB divided by 8, I think is what I'm looking for. Mm, let's see. Don't seem to see it. I think I was looking in the wrong spot. Oh, here it is. Okay, so it was in our PLL library. So I guess makes sense. All right, let me drop this one down. I'm going to mirror this block. Mm, that's what I want. Okay, and let me set this up here. So the clock input here, move it over a little bit. The clock input should be connected to this guy here. And again, even though I'm not using the output of this behavior block, the pin still needs a wire. Otherwise, the whole thing won't netlist properly, and you'll get an error in Spice. So let me copy this. Okay, move it. Didn't land on there. Okay, so let's see. All right, there's another thing I have to be careful about. So the purpose of this is to take the sine wave input and convert it to a different, a digital type of output to drive this divider. So the way I do that is I use this comparator block, which has limiting in it, and uh, that way it will gain this sine wave up to square the waveform, but then it will limit it. Essentially, it's clipping it. So what's going to happen here is, I believe if this is set correctly, that this will clip this will appear as a square wave that clips at 1.8 volts, which is what we want. That's what we want to drive this behavioral block, because our behavioral blocks are set to emulate digital gates running on a 1.8 volt supply. There's some settings for that. Um, so that's what we're doing. And now let's see. So we did that. Now I think is all we need to do is connect back up to we just need to connect back up to the PFD. So let me go ahead and do that. So I will connect this up. And let me rename this node. I'm going to call it VCO clock. Okay, so we unhooked the previous source generator, pulse source generator that was connected to that node. So now that node is floating, which sometimes Spice complains about it. Sometimes if you have an unconnected voltage source like this, an independent voltage source, Spice inserts a resistor so you don't have a node floating. But not all Spices do that, and I don't remember with topspice. So we're going to add a resistor just to be safe here. So let me go to DXSpice and expand on that. Let me grab a resistor. Okay, so you see R underscore horizontal, R underscore vertical. That's the same resistor, but just pre-flipped for you. So I will grab this one. So I want my resistor to point that way. And then I will hook it up. It comes up as 1K. It doesn't matter in this case, so I'll just leave it like that. Okay. And again, the reference designator R question mark. So I do need to annotate my schematic now. So let me go and do that. Okay. Annotate, close. Let me save. It's important to save after the operation. Otherwise, Confirma will be looking at the old version of the file instead of the new one. Hmm. Okay, a quick glance here. It looks like we have everything hooked up. Let's go to Confirma. Let's hit the hierarchy button. So the new hierarchical block showed up. Let me hit fast netlist here. So we're netlisting the whole thing now. Mhm. Okay, it looks like we had a momentary delay there. I think it was another process on my laptop. So anyway, that let me hit that again. Okay, that seems to be fine now. Okay, so we have, I think, the entire phase lock loop. We've got all the behavioral blocks net listed successfully. I think we already have the simulation settings set. And let me go ahead and see how we do here. We're going to do sim netlist. See if it starts up. So it looks like it started up. That's a good sign. Whoops, I don't know what I did. Oh, there we go. So it looks like it started up okay. So we're running out to 5 microseconds, but we have a 1 gigahertz VCO. And I do recall that I was interested in getting a nice measurement on on the jitter. So I think I have the time step. I would crank down on the time step. Let me take a look here. Okay, so our max time step is set to 10 picoseconds, which is pretty tight. So when you first launch a simulation like this and you just want to make sure that your test bench is working okay, you don't need this tight time step, maybe whatever, 100 picoseconds or whatever you think, and then make sure everything is working okay, and then go back when you're satisfied to get a refined measurement. So let me, I'm going to let that run. It's going to sit there and run. And what we will do so that we don't have to wait, we're going to go back to the other one, I hope. Yeah, so this is the one I showed initially. So this test bench was the one we showed initially, and it has already been simulated with a fine time step. So we're going to switch over to this guy temporarily. So I'll do my trusty pass to Confirma. So let's see, pass to Confirma. Okay. And now we got that one going. That one's loaded up here. Let me close this. And we're going to say view plots. So now we're viewing plots to for this simulation, this test bench T underscore KGF behavioral PLL 1 gigahertz out, where the other one was had the underscore assemb on the back end of the name there. So that's how we're making a distinction between the two. So I'm going to plot the loop filter voltage, which is right here. And okay, so this is the capture and lock process for this behavioral phase lock loop. Now you might recall that we selected the VCO frequency to be 1 gigahertz, and it should be 1 gigahertz when the control voltage is 1 volt. So you can see that the loop has settled, had locked up with the control voltage at 1 volt. So this is a good sign. It means that it locked up correctly. And the other thing to point out is this is a pretty fine, if we zoom in here, you can see that the noise on the control voltage there's not a lot of noise there. We can crank the simulator time step down even further. I think we also are using gear integration on this as opposed to trapezoid. That always seems to help a little bit for a simulation of this type. So I would expect that our VCO jitter in the locked state should be pretty good. So let me go and plot the VCO. So We're in top view here, again, top view, new plot, and we'll do VCOP, I think is what we want. So say add. Okay, there's a lot of cycles of the VCO there. And we're going to zoom up. So I really like this top view, except I seem to have fouled that up. Okay, so we have a lot of cycles still. And now I'm going to go over to this transform tool, and it has this eye diagram feature. And so our period at 1 gigahertz should be 1 nanosecond for 1 gig. So this is our data range corresponding to my zoom. I could put something else in here. And then this is my period. If I say OK, here's my eye diagram. So this is, I don't know, what is this, 800 cycles or something of the VCO on top of each other. So if you zoom in, let's say the zero crossing is roughly here. If you zoom in, you can see what our jitter is here, and it's pretty low. And let's see if I can zoom in a little bit more. Okay, and let me put some cursors on that. This is a little tricky. So it's a little tricky getting this because you're not sure which VCO cycle you're landing on. Okay, well, I've already done this, and so I'm going to cheat and tell you what the answer is. It winds up that I think it's around 800 femtoseconds of jitter on this 1 gig VCO. So that's pretty darn good, I'd say. So at any rate, I think we've come to the end. I suppose we could check out how the one that we just assembled, how that one seems to be doing. And let's pause it, and we'll do a partial plot here. And I'm going to plot the loop filter voltage as we did before. Okay, so it looks like it locked up. It's locking up. So that looks like I'd call that success. Close that. So so what did we do? We put together a behavioral phase lock loop running at 1 gigahertz. So we showed how you can do system level type simulations as you would say in like MATLAB or Simulink. We're using behavioral blocks that come with behavioral libraries that you get with ConfirmaXL. Now, one thing I need to warn you about is we're still going through the behavioral libraries and we're cleaning them up. They were originally, a lot of them we originally created in a Mentor graphics schematic tool, and we used some automated software to convert them. And I think it did a pretty good job, but it didn't get everything. So we have to go through and make sure that they work okay, and we have to make sure that they work well on the different simulators that we're targeting. So right now there's 6 different spice simulators that we'd like all these behaviorals to work on. So we're still going through that. Uh, so when you look at the behavioral blocks that are in the current libraries, no guarantees there. They may or may not work. So uh, so I think that's pretty much up. So no transistor level this time around, but we have a nice solid system design, so we're ready to do our transistor level. So the transistor level stuff works pretty good across all the simulators. So it shouldn't be any problem there. So maybe next time we'll do some transistor level of the phase frequency detector or the charge pump or the VCO or something like that. Maybe we'll do some transistor level, and then we'll snap out the behavioral block, snap in the transistor level block, and then repeat the simulation. And that'll give you a good idea of the kind of methodology that we used when using ConfirmaXL. So I hope you liked it. And two, I think it's pretty snappy. The schematics, they load quickly. And you can move from one test bench to another test bench, and do those simulations, reload, confirm XL very quickly. You can move from one to the other very fast, so it's not a lot of waiting, and that's important because as you're working through a system like this, you're building the blocks, and you have a lot of things in your mind as you're doing your design, and delays can really be disruptive to the thought process. So, having a snappy development system, we think is important. So, thanks for sitting in. These things always seem to run a little bit long, but on the other hand, it's not too bad designing a phase lock loop in 30 or 40 minutes. That's not too bad, and explaining new tools as you go. So hopefully you find this helpful, and you'll stop by once in a while and see what we're up to. Thanks again. Bye bye.